this video, we're going to introduce a technique to approximate the solution to an equation. As we discussed all the way back in the section on intermediate value theorem, for complicated equations, solving the equation and finding the exact solution can be time-consuming even for a computer. So you can save yourself some computation time by allowing yourself to approximate the solution. And Newton's method is an extremely effective way to approximate the solution to basically as much of a degree of accuracy as you may want in that scenario. The only cost is that in order to use Newton's method, your function has to have a derivative, and you need to be able to calculate that derivative. But as long as you can do that, this extremely efficient method is available to you. So in the Newton's method scenario, we're trying to solve a solution of the form some expression containing x's equals 0. And that expression containing x's is going to be represented in function notation by f of x. The idea is this. What we're going to do is we're going to start by guessing a possible solution to this equation. Usually we just guess it at random. Let's call that initial guess x sub 0. Now, you might be extremely lucky and that guess might be very close to an actual solution to the equation, but most of the time we're not lucky and that guess is pretty far from the actual solution. So what we're going to do is we're going to take this initial guess and we're going to use it to calculate a second x value called x sub 1. Now x sub 1 may still not be very close to the solution, but it's going to be closer to the solution than your initial guess. So what we're going to do now is take that x1 and use it to construct a third x value called x sub 2, which still may not be very close to the solution, but at least it is closer than the previous x value of x sub 1. And we're just going to keep doing this calculation using x1 to calculate x2, using x2 to get x3, using x3 to get x4, and so on, until it seems like these x values, which we were calculating in succession, are getting closer and closer to a stabilized x value, which is the actual solution. So in order to set up this sequence of x values, which are getting progressively closer and closer to the actual solution, we have a couple of different steps. Step number 1, you're going to need to calculate the derivative of the function f of x on the left side. You're also going to need to choose an initial x value. And in particular, when you're choosing your initial guess for your solution, you need to make sure that that initial guess does not make f prime equal to 0. So now we're going to set up the formula that we can use to successively calculate each of the x values in this little sequence. So I'm going to show you how to take x sub n, maybe this is x4 or x5, and calculate the next x value, maybe x5 or x6. So the current x value is called x sub n. The next x value is going to be called x sub n plus 1. So in order to get the next x in the sequence, take the current x in the sequence and subtract. Subtract what you get when you take the original function and plug in x sub n, and divide that by the derivative with x sub n plugged in. Keep doing this calculation recursively over and over and over again. Use x1 on the right hand side to calculate x2, use x2 on the right-hand side to calculate x3, use x3 to get x4, use x5 to get x6, and so on until, repeat until the next x that you calculate is approximately equal to the x that you started with, x sub n. In other words, repeat until the xn stabilizes. That xn is your approximate solution. If you would like to see an animation, a geometric explanation for where this algorithm comes from and how it works, I've gone ahead and posted that video to our Canvas page. Now let's go ahead and let's actually practice using it. Let's find an approximate solution to the equation 2x to the 5th power minus 8x minus 1 equals 0. So in this problem, the function f of x is given by this expression containing x's on the left side, 2x to the 5th power minus 8x minus 1. And f prime would then be given by 10x to the 4th power minus 8. So the question is, okay, go ahead and try to use Newton's method with an initial guess of a solution at x0 equals 0. Now, suppose that I were going to use the Newton's method formula manually. If I were going to use it manually, I would begin by figuring out the value of the next x in the sequence, x sub 1. I would say x sub 1 is equal to the previous x, x sub 0, then subtract f with x sub 0 plugged in, and divide that by f prime with x sub 0 plugged in. So using the fact that x sub 0 is equal to 0, this would be equal to 0 minus f of 0 divided by f prime of 0. Now it looks like f of 0 is equal to minus 1 and f prime of 0 is equal to negative 8. So this would be equal to negative 1 over 8. That is x1, and to get the next x in the sequence, x sub 2, the next thing that we would have to do is take x sub 1 and subtract f of x sub 1 divided by f prime of x sub 1, which would be equal to negative 1/8. Take away f of negative 1/8 divided by f prime of negative 1/8. But we're only 2 x's in, and this is already getting super tedious. Newton's method is definitely not something that is intended to be implemented by hand. In practice, you're either going to want to set up a script or a short program containing some sort of loop, or you're going to want to use your TI-84. And I'm going to link a video in Canvas and in the description showing you how to implement Newton's method using your TI-83-84. But in this video, what I'm going to show you is how to implement this method using Google Sheets. Because I think of all the options, Google Sheets is one of the few that's freely available and somewhat accessible and doesn't require much coding knowledge. So here I am on Google Sheets. Now in the very first box, I've put my initial guess, which is, in this problem, equal to 0. In the next box, what I'm going to do is I'm going to put in the Newton's method formula that I would use to get the next x in the sequence. But I'm going to try and do it in a slightly clever way so that I can exploit Google Sheets autofillability. This will also work in Excel, by the way. Okay, so for example, in our calculation, to get from x0 to x1, we had to take x0, subtract f of x0, and divide that by f prime of x0. So I'm going to try and take this formula here and type that into Google Sheets. So I'm going to put an equal sign. Equal sign says to Google Sheets, I'm beginning a formula. But then instead of x naught, I'm going to click the box containing the value of x naught. So it filled in, give me equal sign the value in the box which is called A1, first column, first row. So then I'm going to subtract. I'm going to subtract the value of the function f of x with x0 plugged in. Now the function f of x in my problem was given by 2x to the 5th power minus 8x minus 1. So going back to Google Sheets, I'm going to type 2, but not times x, 2 times a1, 2 times the value in the previous box, raise that to the 5th power. Not minus 8x, but minus 8 times the value in a1, minus 1. I'm going to take that entire expression representing f of x naught, and I'm going to divide that by f prime of x naught. Okay, f prime of x naught would be given by 10 times, not x to the 4th power, but 10 times the value in a1 to the 4th power, minus 8. Now that I've finished filling in this formula, I'm going to hit enter. And sure enough, that's the value of negative 1/8, the value of x1 that we calculated by hand. But as a result of taking the time to enter the formula in this fashion, we have unlocked the ability to use Excel's autofill feature. So I'm going to highlight the box containing x1, and I'm going to look at this little square in the bottom right. I'm going to move my cursor over it until the cursor forms this sort of crosshair, and then I'm going to click and hold and drag down until usually maybe 15 or 16 will do. And what this does is it fills in the value of all the different x sub n's. Here's x sub 0, here's x1, then x2, x3, x4, x5, x6, and so on. Autofill feature has filled it all in for me. Now the values have stabilized extremely quickly. They stabilized basically as soon as we hit x2, x3 to a value of negative 0.12500763317. Already, this approximation is extremely accurate to, looks like 10 decimal places. And that's basically because that is the default number of decimal places that Google Sheets will display. It is possible using this method to get even more decimal places. For example, if I force Google Sheets to display even more decimal places, we can see even more degrees of accuracy. This time at around x sub 3, it stabilizes at this value. I'm not even going to try to read it. Okay, now here's a practice that I strongly recommend. I strongly recommend that if you're doing more than one of these problems, that you take all the boxes that you auto-filled, starting from row 3 and down, and you erase what's in those boxes. It's really easy for me to forget, if I'm doing more than one of these problems, to do the autofill process again for when I'm doing a different function. So I just delete those every single time. Now in part B, they say, okay, don't change the function, don't change the equation, but just change the initial guess to x0 equals minus 4. Let's see what happens if we change the initial guess to something that's quite far away from x0 equals 0. I'm going to go into the first box and replace my initial guess with negative 4. And the formula that we entered for the second box is still valid because the actual function f of x and its derivative hasn't changed. So let me go ahead and autofill again, maybe down to 17, and notice that this time the values have stabilized at a different location. This time they've stabilized at a value of x that is equal to negative 1.381 and some change. So was one answer correct and the other answer wrong? No, not exactly. The thing is that this equation here, 2x to the 5th power minus 8x minus 1 equals 0, this equation has multiple solutions. We can confirm this by looking at a graph of the function 2x to the 5th power minus 8x minus 1. Where does this function output 0? Where does this function cross the y-axis? It crosses the y-axis at it looks like 3 different locations. Now when we guessed x equals 0 for our initial starting location, we arrived at the solution which was approximately equal to negative 1/8. But when we made an initial guess that's all the way over here at x equals negative 4, we converged upon this solution, negative 1.8381. So depending upon your initial guess, you may converge upon a different solution than someone else, and that's just because there are multiple solutions available to this equation. So let's try it again with this exercise. Let's estimate a solution to 3 sine of x squared equals 2. Now, the possibility is pretty good that this equation has more than one solution, but that's fine. Just estimate the value of any solution you happen to stumble across. Now, in order to set up to use Newton's method, the first thing that we need to do is rewrite this equation in the form something equals 0. So the first thing that I'm going to do is subtract 2 from both sides. Now I can see that the function I'm working with is given by 3 sine x squared minus 2, that function on the left-hand side, whose derivative is given by 6x, 3 times 2x, cosine of x squared. So now that I've got the equation in the right format, I've identified the function and I've found the function's derivative using chain rule. It's now time for me to apply Newton's method. Now in this problem, they have not given me an initial guess for the value of x0. So I'm going to have to pick my own value of x0. Now, in general, my first inclination is to try x0 equals 0. 0 is one of my favorite numbers, so why not try that first? The problem, though, in this situation, is that if I pick x0 equals 0, and I try and plug that value into f prime, then I'm going to get 0 times 6 times cosine of 0. 0 annihilates everything around it, so this is going to be 0. So that's going to create a problem when we try and calculate x1, because it's going to cause me to divide by 0 in the calculation at x1, which is going to cause an error. So I'm going to need to choose a different value of x0, a value of x0 which is specifically going to ensure that f prime is non-zero. So maybe x0 equals 1 will be better in this situation. And as usual, the first thing that I'm going to do is basically just clean everything out. Nothing left over from the previous problem that can cause interference or problems of any kind. So now I'm going to put my initial guess, x0 equals 1, into the first box. And into the second box, I'll enter a formula. Equals the x0 from before minus the value of the original function with a1 replacing x wherever it appears. So not 3 times sine x squared minus 2, 3 times sine a1 squared minus 2. Then I'm going to divide that by the value of f prime with all the x's replaced by a1's. So not 6 times x, 6 times a1. Not cosine of x squared, but cosine of a1 squared. So it has extrapolated the value of x sub 1, and let's autofill to get the values of the other x's. So by highlighting the box A2, putting my cursor over the square in the bottom right, click, hold, drag down, we get an approximate solution which seems to stabilize at around 0.85424,09825. So this would be the estimated value of the solution to this equation. Again, the major advantage over other methods is how incredibly accurate this estimation is. Let's try it on some slightly less standard problems. Let's see if we can estimate the value of the fifth root of 3. In order to be able to apply Newton's method, I need to be able to re-express this problem as finding the solution to f of x equals 0. So, the fifth root of 3 is the solution to what equation? Now, one thing I know for sure about the fifth root of 3 is that if I take it to the fifth power and the fifth root will cancel, and 3 will be the result. So the fifth root of 3 is a solution to x to the fifth power equals 3. If I plug fifth root of 3 into that equation, it becomes a true statement. So I'm trying to estimate the value of the solution to x to the fifth power minus 3 equals 0, which reveals that f of x for this problem is 5 is x to the fifth power, and its derivative is 5x to the fourth power. Let's choose an initial guess. Now once again, x0 equals 0 is not going to work in this problem, because if I choose x0 equals 0, that's going to cause the derivative to output 0, which is going to cause a division by 0 error. So in order to avoid that, in this problem, I'll try maybe an initial guess of 1. So either you can go to your 84 if you watch that tutorial video, or you can join me here on Google Sheets. If using Google Sheets, be careful to clean everything out from the previous problem. Let's go ahead and enter our initial guess of 1, and let's go ahead and enter our Newton's method formula. Equal sign, previous value a sub 1, minus the original function, not x but a1 to the fifth power minus 3. Then divide that by 5 times not x but a1 to the power 4. Hit enter. Then highlight that box. Click the little box in the bottom right. Click, hold, and drag down to autofill. And it looks like we stabilize at a value of around 1.2457. This is something that you can check as well. If you take 3 and raise it to the power 1 divided by 5, then you get the same result that we got via the Excel spreadsheet. Final example. Let's try and estimate the location of a critical point of the function given here, this giant polynomial. So in other words, we're looking for locations where the derivative of this giant polynomial, 6x to the fifth power minus 5x to the fourth power minus 24x to the third power minus 2x plus 1 is equal to 0. Solutions to this equation would be critical points. So, I have no interest in solving this equation by hand, not at all. So let's go ahead and set f of x equal to this expression containing x's on the left side. The derivative of this function on the left side would be equal to 30 x to the 4th power minus 20 x to the 3rd power minus, 72 x squared minus 2. Now in this case, using an x naught that's equal to 0 will be viable, because if I plug 0 into f prime, the result will be negative 2, so I won't be dividing by 0 at any point. So let's go ahead and stick this big mess into either our TI-84 or into Google Sheets / Excel, whatever you happen to be using. Alright, off screen I went ahead and typed that big mess in. Here is the formula for f of x with x replaced by a1, and here's the formula for f prime with x replaced by a1. So now let's autofill, click, hold, drag. Okay, and it looks like our critical point is located at approximately 0.265897771. Now, does this function g of x probably have other critical points? Yes, it probably does. We would find them by trying different values of an initial guess to see if we got different approximate solutions. For example, I might go back here and try a vastly different x, maybe an initial guess of 5, and we can see a convergence upon another critical point at 2.47, approximately speaking. If I change my initial guess to something like minus 5, then that would change the result to negative 1.66. So by changing the values of the initial guess, you can change the approximate solution that you obtain. That concludes today's material. We introduced a method which was called Newton's method, which is a way of using the derivative of a function together with a recursive formula to approximate a solution to an equation.